GNSS WASP wide area spoofing attack on satellite navigation. So the idea of this project was to identify a weakness of these GNSS systems. Now there are various assumptions that have been made about defenses. And we decided a few major assumptions. We decided to question them a little more in depth. And yeah, this WASP project came out of it. Well, first of all, GNSS global navigation satellite systems. We've all used it. We use it in our daily lives, navigation. It's used in aircraft shipping, also in more industrial settings, which require higher levels of precision, farming, for instance. But what is also an interesting aspect, we say GNSS, we always think of positioning, but that is not the only thing it can do. It also provides a very accurate source of time. And this source of time finds wide use in industrial systems, SCADA systems, especially to monitor, let's think of gas pipelines, oil pipelines, power networks. These are systems which are very widely distributed geographically, and operators might want to be able to correlate events that happen across an entire continent, and to do that, precise source of time is required. And for this, systems like GNSS-based clocks are used. So this is a very useful system. Sadly, as we've seen in the last few years, GNSS spoofing and jamming, an ongoing and growing threat. You can see this map on the left. That is from 2 days ago. This map is generated by civilian aircraft. They report their position, their speed, and so on using ADS-B. And these systems also report the quality of their GPS log. And this allows to get almost, let's call it real-time maps of where spoofing is happening. Big issue with spoofing and jamming is these attacks have become much more widespread. The techniques to perform them have improved. The costs have gone down, and this has become a big threat against which already existing countermeasures have been developed. But what we aim to show is that these are not sufficient, and we show this with WASP. We break the existing assumptions about these defenses. We show that with few strategically placed attackers, so 4 or more, we can get an attack which is effective of a large area. And this attack crucially maintains relative distances between victim receivers. And not only that, it also preserves an authentic angle of arrival of the incoming signal. Now we see in recent GNSS receivers, those that are more aware of these kinds of threats, usually they use arrays of receivers and try, thanks to null steering, to ignore spoofed signals. These techniques would not be as effective with under a WASP attack. And so the solutions are receivers must aggregate measurements over time to detect, and they must either move or cooperate in order to have a chance for detection. Now let's take a step back. How does GNSS work? Well, we have a ground segment. This ground segment monitors the satellites. It monitors their orbits. It sends metadata and corrections to them. Just to give you an example, when a satellite first enters service, for the first year, more or less, the clocks tend to run a little fast on the satellite platform, on the GNSS satellite platform. And this has to be corrected. And and this is done by the ground segment. Well, the ground segment then communicates with the space segment. We have our satellites. In our work, we focused on GPS and especially on the L1 GPS signals, the most basic, the traditional GPS signal. And exactly, our focus was mostly on the physical layer of things. So we didn't look into altering the contents of messages, but purely altering positions of transmitters. So how does GPS signal look like? So there is a L1 carrier in this specific case, and over this carrier there is a so-called coarse acquisition code. This coarse acquisition code, also known as golden codes, if I'm not mistaken, is used by receivers to get a lock on the signal. Essentially, the satellite is at 10,000 kilometers above the surface of the Earth. And in order for, and when the signal arrives on Earth, it is so attenuated, it is at barely at the noise floor. And the only way of identifying and tracking this signal is being aware of this coarse acquisition codes and then performing a small search in order to lock onto a signal. On these coarse acquisition codes, a navigation message is modulated, and this contains orbital parameters, various corrections, and so on and so forth. And lastly, we have the user segment. The user segment is often thought of as cheap components with not so reliable clocks, and these are then able to receive the GPS signals, synchronize their clocks, and get their position. So essentially, they read the orbital data and metadata. They read in these messages the send time, and then also have the time delta of the arriving signals. With this, they can derive pseudo ranges to the various satellites. And lastly, they are able to compute both their position, XYZ, and time. Good. So let's get a little bit more in depth. Spoofing attacks, how exactly do they work? As you can see in this little diagram, we have two satellites, S0 and S1, and they're transmitting their signals to two receivers on the ground. Due to the geometry of the receivers, the one on the left first gets navigation messages from satellite 0, then satellite 1, while the one on the right just the opposite. A spoofing attack might look as follow. We have an evil attacker, and they start by jamming the signals, introducing a noise in the RF spectrum. And this makes the receiver lose lock to the original signals. After this is done, the attacker starts transmitting their own signals. They might alter the navigation messages. But as you can see here in this example, with a single transmitter, since the job it does, it takes a signal from satellite 0, signal from satellite 1, it combines them and sends them from its one antenna. The time offsets in arrival time will be fixed. And so suddenly the two antennas will receive navigation messages with the exact same time offset. So what's the result of that? Well, you can see here, it's the example on the left, and that is our single attacker broadcasting to an arbitrary number of receivers. And the effect this has is every receiver will compute the same position. So every single receiver will believe it is at the same place. And this gives us already the key to identifying these kinds of attack. And the way this usually works, now you can see here on the right in the little plot, that is 4 receivers. They might not know their exact geographic position, but what they definitely know is their relative distance. One can imagine if you have a container ship, and you have a receiver at the front and at the back, the container ship knows exactly that these two receivers are at a specific distance, but it might not know its exact position. And so what it does, what potential victim can do is they have the distance measurements they derive, and whenever these distance measurements suddenly collapse to zero, that is a very good indicator that an attack is occurring. So how can an attacker defeat this kind of defense? Well, the solution is to, instead of broadcasting the signal, to very accurately send one signal to one receiver. So each receiver gets their own signal. This has a bunch of advantages. Now, each receiver can be steered around at will. The issue is the number of attackers has to scale linearly with the number of receivers, and a smart defender might hide some receivers in such a way that an attacker is not aware of them. And in this fashion, they could identify that something is off. So this second strategy also is second attack strategy is also not immensely effective. There are good countermeasures. So the last kind of strategy is to use multiple transmitters, and these send signals which are then received by multiple receivers. The main challenge with this is, as shown by Tiffenauer et al., is that the more receiver one cooperating receiver one tries to spoof, the trickier the positioning of the attackers become. In an ideal scenario, now when there are two receivers, the position of an attacker is constrained to this paraboloid. With 3 receivers, it's constrained to this curve in 3D space. And with 4 receivers, an attacker's position is already constrained to only 2 places. So it seems like this kind of approach, using multiple transmitters against multiple receivers, might not be the best solution. And this leads us to the so-called generalized spoofing problem. Now, single static receiver, that is easy to solve. You use a single attacker. But how can we attack these larger group of receivers? And the main solution we've come up with is that the constraints, those apply only in an ideal scenario. And luckily, sadly, we're in the real world. And so a lot of the ideal goes away. Now, just to remind you again, the signal from the satellite has to travel 10,000 kilometers to get to us. It has to traverse the ionosphere. It has to traverse the troposphere. There is small mistakes in the computed orbits. Whenever there is multipath, there is errors are unexpected fact of life, and this is what we exploit in our attack. Exactly, to reiterate, with only 4 strategically placed transmitters, we are effective against an arbitrary number of victims within the so-called area of effect of our attack. These receivers will preserve their relative distances, their movements will also be preserved, and now since we are essentially hiding our attack in errors, we will always introduce a small systematic error, but this can be quite small and tough to detect. So what we've done, we've set up the theory. Not only that, we've also set up an experimental setup. We use 6 USRPs, software-defined radios, and we try to keep them as independent as possible. Due to regulatory constraints, we cannot just broadcast spoofing signals, in the air. So what we've done is a purely wire-based setup, but each of the transmitters in the box labeled with A is operates fully independently, and I think it demonstrates that the feasibility of such an attack in the real world. Exactly. And lastly, we broke things, so we also got to find a solution, and we have proposed a few different ways to which are aware of these kinds of attacks to detect spoofing, and yeah, we've evaluated it. So GNSS WASP, how exactly does this work? You can see here you have receiver, GNSS receiver. Let's say it's located in Los Angeles, and this receiver sees 2 satellites. And this is a regular occurrence, nothing weird going on here. What we have here is a second set of receivers. Let's say these are located in Zurich, and these are our victims for our attack. Now we have receiver 0 at the little R triangle. That's our reference position. That's the center of the volume of our attack. And RJ is an arbitrary receiver which is located nearby, which we also want to spoof. So an ideal attack would look as follows. We would just take the 2 satellites and shift them over from LA to Zurich. As you might imagine, this is not immensely feasible, and this leads us to the compromise we make. Instead of putting our transmitters in orbit at the position of the real satellites, we attach them to drones and we put them as high up as possible as we can over our victim receivers, but still within a reasonable distance. Let's say we tested it from 300 to 5 kilometers of altitude above the victim receivers. And here you might already spot the source of some errors that make our attack detectable. For the receiver at the reference position, if done ideally, this attack would not be able to detect that anything is off, because as you can see, the paths match the real ones. While the further one goes from these 2 attackers, the more noticeable a potential error becomes. Let's look at this systematic error. You can see here on the left the simplified diagram, and the satellite is the ideal satellite, so the place where we would want to put our attacker S1, and the R is the center of our attack, the reference location, and our attacker is located along this axis. And on the left, VI is an arbitrary receiver I, also affected by the attack. And the further it goes from this line, the bigger the error becomes. On this little map, you can see on the left, you have one single receiver. It's moving around following the red trajectory. And the trajectory it computes thanks to GPS is the blue one. So you can see if the single receiver is using an IMU, for instance, and validating its GPS position using the IMU, then this would already pretty closely match. And similarly, for the 2 receivers on the right, we can imagine these are receivers at known fixed distance. They once again move along the red trajectory. And essentially, the derived position under attack, the blue line, still mostly preserves the distance between the 2, making detection a little trickier. So what are the parameters that dictate how big this error becomes? It's 2. One is the distance a receiver is from the reference position. So the further we are, the bigger the error will be. And secondly is how far away we can pull an attacker. Now, if the attacker is very close to the reference position, to the center of our attack, then errors grow very quickly with distance from this position. While the further we are able to put these attackers, the slower the growth of error will become. Interesting facet is this error will never grow faster than linearly. The reason for that is if we start looking from enough distance at this attack, if we're far enough, even though we're using multiple transmitters to a receiver, this will almost look like a single transmitter spoofer. And so the error will only increase linearly with the distance. Exactly. So after setting up the theoretical framework, we started doing some experiments on physical hardware. And you can see here on the very left of the plot, position A, that is the center of our attack. And the further we go, the bigger the difference between the actual receiver position and the computed position there will be bigger and bigger errors. And one can think of an ideal attacker, and an ideal attacker, the derived position and actual position would always match. So we essentially validated that the simulation we've done matches our models and matches the experiments. What you might notice here, unsurprisingly, experimental data is showing a bit bigger variance. And the main reason for that is the synchronization of the sex-independent USRPs. So we could have used octoclock, connected them all to the same clock source in order to have good synchronization. We decided against this. We decided to use GPS disciplined oscillators as clock sources because, as mentioned before, we wanted to showcase that such an attacker is feasible when the transmitters are geographically quite distant from each other. No? So in the case of a real attack attached to drones. And exactly, so what we've seen is when the clocks get properly synchronized, then we get a pretty tight area. And when these synchronization does not happen, we start seeing drift in the derived position because each of these radio is impersonating a satellite. And if it runs a tiny bit faster or slower, this will affect the time of arrival of the signals. A fun tidbit, we did these experiments in summer. And the heat in summer actually affected the clocks so much that we had to wait for night time in order for the oscillators on the USRPs to reach their happy temperatures and in order to give good and reliable results. Good. So this was the implementation. Now let's get to the countermeasures. Countermeasures, we always need to make some assumptions. What is a victim receiver able to do? Well, a victim receiver, we decided, has to have a known non-spoof data set to set various thresholds. It should only be able to detect this attack by evaluating relative distances between antennas. So we imagined the receivers are fixed, and they know the distances between each other, but they might not be aware of their geographic position. And they then pick an acceptable false rejection rate. What we've done, just to illustrate a little better detection strategies, is set this false rejection rate at around the false alarm once every 5 minutes, which is very excessive, but this is how we decided to visualize it. And lastly, the data sets we evaluated comprised around 10,000 measurements, which amounts to more or less 15 minutes of operations. So on the countermeasure side, we started very basic, just checking the ratio of outlier in receiver distances. So the idea would be receivers take a known good data sets. They set their threshold such that the false alarm rate is at an acceptable level. And then during an attack, the number of outliers would grow enough to trigger an alert. How does this look in the case of a real attack? Well, you can see here, this is a map of the attack. The red triangle, that is the center of our attack. And you might notice the whole area is a little shifted. And the reason for this is the area where our attack is effective is also strongly dependent from the position of the satellites, of the transmitters. Now, if all the satellites are a little lower over the horizon, this might affect the shape of the effective area. If we happen to pick a set of transmitters which are located more towards the north, this will also affect the area where the attack is effective. What you can see here is that this strategy of purely checking ratio of outliers, it leaves with one alert, false alert every 5 minutes, it leaves quite a big area where no attack is detected. And so we had to do a little better, and already better results came in with using rolling windows now, because the regular signal, there is quite a bit of jitter. And by using a 1 second rolling window, the area where our attack is effective has greatly reduced. Exactly, but where we found the best result is with a QSUM detector, cumulative sum detector. As a reminder, the QSUM detector, it takes a specific measurement of a distance and removes the expected error and the distance from this measurement, and this gets aggregated over time. And in a spoofing scenario, the idea is that this aggregation will lead at a certain point to the exceedance of our alert threshold, while the non-spoofing scenario will always comfortably stay below this threshold. And as mentioned, with this, we found the best results. So to recap, the first strategy, while the easiest, is not very effective, only able to detect attack over longer distances from the center of the attack. The second identifies attacks more reliably. It sacrifices, debatable, a little bit of detection time for its greater accuracy. And lastly, the QSUM detector, as you've seen, outperforms the other two by quite a bit. But it also has a few issues, like a long time to trigger an alert after spoofing has started, as well as its inability to detect attacks where the 4 receivers are very close to the center of the attack. The reason why this is, as you might remember, when the receivers are very close to the center of the attack, the error that we introduce is quite small. And so in this scenario, even QSUM would be unable to detect the attack. Well, this brings me a bit ahead of schedule, but all good, to the takeaways. And the main takeaways I'd like to give you is that such an attack is effective over a wide area, multiple receivers. You can imagine, for instance, drone swarms. Those can also be affected by such an attack. Not just that, but also the spoofing signals will arrive from the quote-unquote correct direction, the expected direction, and so no steering and these kinds of strategies would lose effectiveness. The saving grace is that errors increase with distance from the center of the attack, and this opens the door to various detection strategies. The main challenge now is to identify these kinds of attacks. Receivers must either cooperate or move. They must be aware of their normal operation error rates. And what is important, the larger the area they cover and the more sensors one is able to use for detection, the more effective these various detection strategies become. And that would already be it. Yes, I would say thanks for your attention, and I'd be open for any and all questions.